So, free radicals. What are free radicals? Where do we find them? How do they impact? Why do they suddenly come up in health? How do they impact on health? And I think importantly is, as chemistry students, what can we learn about chemistry by looking at free radicals? Let's be chemistry students and look at some chemical reactions. We have water dissociates into the hydrogen ion and the hydroxyl ion. It has a pKa of 7, which means that there's 10 million of waters for every hydrogen ion. So free radicals, well, hydrogen ion's a free radical? No, actually it's not. This is a reaction that I'm particularly sensitive about. The silver ion reacts with chloride. Silver ion actually reacts with just about every anion there is. The silver ion reacts with chloride to produce a white precipitate, and it's used in a titration for chloride. In my early days as a lab tech, I did this as a titration. When the silver goes into excess, it reacts with chromate and produces a red precipitate. So you titrate to a red endpoint. This is for sodium chloride in salt, and it can be used also in environmental analysis for the presence of sodium, the presence of chloride as a pollutant. And then, so where are the free radicals? Well, chloride, is that a free radical? Silver, is that no free radicals. Okay, let's look at carbon dioxide dissolves nicely in water to form a bicarbonate, and then the bicarbonate further dissociates to form a hydrogen ion carbonic acid. And it's very important for the transport of carbon dioxide for the blood, and it's important for pH control of the blood, a very, very important reaction. And this, of course, relates to the fizziness of soft drinks and beer. And so where are the free radicals? Well, no free radicals. This is all about the octet rule. Everything meets the octet rule. The octet rule is met on the reactants, and the octet rule is met on the products. So that the hydrogen ion is stabilized by being an ion. And the chloride is stabilized by being an ion. And so chemical reactions are not about anions and cations. They're about meeting the octet rule, which is not late-breaking news, and I know that. But I think it kind of emphasizes that chemistry doesn't have very much to do with the anions and the cations exactly. It has everything to do with the octet rule. So where do we find free radicals? Well, we're not making much progress. Let's look at the periodic table. We want to find free radicals. Look at the periodic table. The periodic table is all about free radicals. Perhaps the most reactive compound in all of science is the hydrogen as it sits on the periodic table. Hydrogen as it sits on the periodic table has a proton and an electron, and it violates the octet rule, the duet rule in the case of hydrogen. It's like the hydrogen either wants no electrons, which will give it a positive charge, or it needs to be combined with a covalent bond with something else to give it the electron it needs. Hydrogen is the most common element in the universe, and it exists in nature as a diatomic gas, which fulfills the octet rule, again, the duet rule in the case of hydrogen. So oxygen, let's take a look at oxygen. Oxygen is, as it sits on the periodic table, is a reactive particle to the point that it never exists. There's no oxygen exists as a free radical, but not the way it sits on the periodic table. Oxygen has 2 unpaired electrons as it sits on the periodic table, and is kind of an imaginary particle, actually. The hydrogen free radical does appear in cells sometimes, and oxygen does the same thing that hydrogen does. It forms a diatomic molecule. So oxygen is O2. O2 is its stability, comes from forming a diatomic molecule. And then nitrogen is even more extreme. Nitrogen now has 3 unpaired electrons and forms a diatomic gas with itself, so N2. And N2 is actually one of the more stable compounds that we ever encounter. Nitrogen gas is like very close to an inert gas. It's very unreactive. Chlorine forms a diatomic gas. Fluorine forms a diatomic gas. Sodium is a free radical as it sits on the periodic table and can exist as a metal, but it's extremely reactive. And I've never seen sodium as a metal. I know it exists, but I've never seen it before. So where do we find free radicals? Well, I'm a chemistry student, and I've taken chemistry classes all the way to the top, and I'm going through, sorting through my rather muddy mind, and I'm free radicals. It seems like free radicals are intermediates in reactions or something. I don't know. So I go to Google, and I come across an article about free radicals from the Khan Academy. The article is about the reaction between methane and chlorine gas. Chlorine gas. Chlorine as an atom is a free radical, but it forms a chlorine gas, which is Cl2, and then methane is natural gas. It's a fairly common material in our society, very common material in our society. If you heat them up together, the first thing that happens is the chlorine breaks down first. The chlorine is less stable than the methane. The chlorine breaks down into a free radical. Finally, we have a free radical. The free radical has a half-life of a billionth of a second. Okay, a billionth of a second. It turns around and it attacks the methane, and it just jerks a hydrogen right off of the methane. This is the hydrogen, the proton, and the electron both, and it forms hydrogen chloride. And then it leaves a scar on the methane, and the scar will typically be filled with another chlorine free radical. So the free radical on the methane and the free radical of a different chlorine will combine and form hydrogen chloride. And then the methane free radical might combine with another methane free radical, and if it does, it'll produce ethane. But the reaction basically is methane, chlorine gas. If you heat it up and heat it up and heat it up, the chlorine gas breaks into a free radical, and it produces hydrogen chloride and methylene, hydrogen chloride and chloromethane. And these reactions are really quite familiar in chemistry. The reaction diagram would look like this, and they're pretty much always the same. The products are at a higher energy. Cross that out. The reactants are at a higher energy than the product. So the rule in chemistry is that the energy always has to be going downhill. So the methane and the chlorine are here, and the methane and the chlorine are here, and the hydrogen chloride and the chloromethane are the products. And the energy of activation is this guy. So this is the heat that makes the reaction happen. And at the very top of the curve, we have chlorine is a free radical. So, and chlorine is a free radical, they say has a half-life of a billionth of a second. Okay, I'm in high school when I see this for the first time. And I look at this graph, the teacher has it on the board, and I say, so what's the x-axis? He says, well, that's the reaction coordinate. And I say, it must be time. And he says, well, it's the reaction coordinate. And I say, it has to be time. And he says, well, it could be time. So I assume the guy's an idiot and kind of don't worry about it. But let's back up and look at the free radical. The free radical has a half-life of a billionth of a second. So is a billionth of a second the same as zero? It's kind of an important question. If the billionth of a second is a billionth of a second, then this truly is a time. It's quick, but it's a time. Now, if the billionth of a second is zero, then the reaction coordinate is not time, and the free radical becomes an imaginary construction of human imagination. The free radical becomes a construction from the quantum mechanical model to help us understand things that we may never be able to understand. It's not a big deal, but I think it's interesting. So let's take a look at a biological example. It could have been anything. I've somewhat arbitrarily picked this one. This is the glycolysis of glucose to ethanol. So the high energy glucose reacts in a very complex way, much more complicated than the chlorine gas, and it produces, the high energy glucose produces lower energy ethanol and 2 ATP. So it has to be a downhill reaction, and it is a downhill reaction by virtue of the energy that comes from the glucose. And the same rules hold. I mean, this is on a thermodynamic level. This is not really different than the chlorine and the methane. You have the same energy of activation. Now recall, of course, that the energy of activation is lowered by the enzymes. The enzymes are catalysts, and they lower the energy of activation. There's still free radicals at the top, and my guess is that there's many free radicals, but they probably have a half-life of a billionth of a second. So a lot of the same stuff holds here. This is the same as the methane and the chlorine gas, except for there's one major difference, and that is that the chlorine and the methane, you got to heat that up to about 400 degrees centigrade. This reaction happens at room temperature. If it's a mammal or a bird, it happens at precisely 37 degrees centigrade. There's no extreme conditions here. This is biochemical reactions. Every biochemical reaction is like walking along the edge of a razor blade. You can fall one way or the other. Unlike the methane and the chlorine gas, it's like you got a radical top of the peak. This is not a radical top of the peak. The concept is the same, but it's not like a steep drop-off, kind of as a symbolic image. It's not a steep drop-off on both sides. And the result of this is that free radicals leak out sometimes. Especially reactions with oxygen are very problematical. Oxygen is a nasty chemical, and things that involve oxygen tend to leak free radicals. Things especially like regular anaerobic respiration and photosynthesis. The free radicals just, I mean, it's kind of you're kind of walking along the edge of a knife, and sometimes things just kind of fall off. They shouldn't fall off. And this problem has gone back to the very beginning of life, which is a billion years ago. So the issue of free radicals has always been around, and organisms have developed tools to deal with the free radicals, which are antioxidants. So the antioxidant systems go back to the very beginning of life. Free radicals have been around like forever, and higher organisms, and I would say this includes all higher organisms, have taken the free radicals and used them into tools. I mean, they've got them, evolution being what it is. Free radicals have been made into tools for all kinds of things, and free radicals serve all kinds of purposes in higher organisms. But in the end, I think it's fair to say that they're kind of like garbage that shouldn't be there. So free radicals only come about in biological systems. You don't find them anywhere else. And I think important is that, like as a personal statement, I've gone down this road looking at free radicals, and I've learned all kinds of things about quantum mechanics, about chemical reactions. My knowledge of chemistry has exploded because of my study of free radicals.